Welcome back to ECE 320A. In this video, we're going to be first stating the final value theorem. Then we will show why we can believe that expression that we use to perform the final value theorem, and we'll go ahead and illustrate the final value theorem with some examples. Sometimes we may not want to actually find the complete solution to our problem. Maybe we just want to know, where did we start, where did we end, what's the initial value of the time function, or what's the final value of the time function. That then can be determined if the initial value theorem or the final value theorem can be applied. And the beauty of these theorems is that we don't have to go through maybe the process of explicitly finding the inverse Laplace transform exactly. What we can do is simply work with the transform expression directly and quickly, with some limiting arguments, determine what, if it's applicable, what is the initial value and what is the final value of this particular expression given by a given transform. Let's state the final value theorem. There's two conditions that need to be true or satisfied before we can apply the expression or the equality that is the final value theorem. So here's condition one. If x of t and x prime of t are Laplace transformable, that means they're well behaved. That means there's something like exponentials, there's exponentially damped signs, there's ramps, etc. They're not e to the t, for example. That may not be well behaved. So if we have x and x prime that are Laplace transformable, and those are usually typical realizable signals in our circuit problems, and the expression, the transform S times capital X of S, has no poles on the j omega axis or in the right half plane, then we can apply the final value theorem, which says that the limiting value of the time domain expression, x of t, which means what is x of t going to become or equal or approach as t goes to infinity, that's in fact equal to the limit as s goes to 0 of s times capital X of s. That's the final value theorem, and it can't always be applied. It has to, and usually the condition that is not, or the condition that is violated, is condition 2. We have one pole on the j omega axis or in the right half plane. It only takes one pole, and now it's good that we've defined what a pole actually is. Here's a justification of that equation. For notation reasons, let's assume that little x of t Laplace transforms into capital X of s. If that's the case, then we know what the transform pair, the Laplace transform pair, looks like for the derivative of x. X prime of t has a Laplace transform s times capital X of s minus the time domain expression's value at time t equals 0 minus. That's what x prime of t is when we Laplace transform it. Now, starting with that, on the left in blue, we have the Laplace transform of the derivative, which is s capital X of s minus x of 0 minus. We're just restating what that is. That's the Laplace transform of x prime of t. But by the definition of the Laplace transform, and this is a one-sided Laplace transform, that's why that initial condition is there, that's the integral from t equals 0 minus to infinity of the waveform that we are Laplace transforming, which is x prime, scaled by this exponential function dt. So we're sort of looking at the correlation between the derivative of x and this exponential, complex exponential waveform, which really you can sort of think of as exponentially damped and exponentially unbounded sines and cosines, how do those correlate with x prime? That's really sort of what you're condensing into the Laplace transform expression. Let's now move or add x of 0 minus to both sides of this particular equation. And really, it's more, let me not include the definition. We're really now looking at this expression. Let's now add x of 0 minus to both sides. That's in blue in the next line, but then what we want to do is look at the limit of both sides as s goes to 0. On the left, we aren't going to do anything. We're just going to leave that expression intact. That's the limit as s goes to 0 of s capital X of s. That's now equal to the limit of this integral from 0 minus to infinity of x prime e to the minus st dt plus x of 0 minus. X prime is just dx dt, but that then, if you simply look at dx dt dt, that's now the integral of dx, which just integrates to x, and we need to evaluate that at the lower limit and the upper limit, or we now have, for a result of performing the limiting operation on that integral relationship inside the curly brackets, we now have x at infinity minus x at 0 minus plus x of 0 minus, but that's just x at infinity, or the limit as t goes to infinity of x of t, which then says that what we have here on the right is equal to what we have on the left, and that's our final value theorem. The limit as t goes to infinity of x of t, that's this, is equal to the limit as s goes to 0 of s x of s. Again, assuming that these conditions in the theorem are true, that x and x prime are Laplace transformable or well behaved. We sort of assume that's true, but then we need to make sure that this transform s x of s has all of its poles in the left half plane before we apply this relationship. Let's see if we can now use that, or when we can't use that, associated with particular transform expressions. Suppose we look at capital V sub 0 of s equaling minus 4 in the numerator, and the denominator is 2s squared plus 3s plus 1. We wouldn't have to factor out that 2 from the leading coefficient, but let's go ahead and do that, and then that allows us to, with a quadratic, very quickly determine where or if this quadratic corresponds to stable roots. If you have a quadratic that's monic, so here this is monic, so everything inside the parentheses, that's representing a monic polynomial, which means for that quadratic we only have 2 coefficients that are not set or that are variable, and as long as those 2 coefficients are both there, so I call that present, and as long as they are both positive, then we know that we have roots are in the left half plane, where LHP is the left half of the complex S plane. LHP then is LHP. So the roots are in the left half plane, since a quadratic and 3/2 is greater than 0 and 1/2 is greater than 0. And we can then do that, or make just check those because we factored it to be a monic. So that means then that the poles of S v sub 0 of S are stable, and stable means that it's in the strict left half plane, nothing on the imaginary axis. That means now that we can, in fact, apply the final value theorem, which now says that the limit as t goes to infinity of v sub 0 of t is equal to the limit as s goes to 0 of s v sub 0 of s, and that's now the limit as s goes to 0 of minus 4s over 2 times s squared plus 3/2 s plus 1/2. And now what does that do in the limit as s goes to 0? Now as s goes to 0, we see that the denominator is well behaved. We have 0 plus 0 plus 1/2 scaled by 2, so we have 1 in the denominator, and we have 0 upstairs. So in fact, the final value theorem says that v sub 0 of t will approach 0 as t gets large. So based on this particular starting transform for capital V sub 0 of s, we can now, without inverse Laplace transforming, without finding the exact expression for little v sub 0 of t, we can conclude by applying the final value theorem that the final value of little v sub 0 of t is going to be 0. Let's look at another example. Suppose now we look at capital X of s. Now what can we say? Well, we know that one of these poles is at the origin, but we also want to see what's happening with these poles. Well, it's monic already, which means we just need to focus on the linear coefficient and the constant coefficient. These are present and positive. Which means that they are stable, or that they're in the left half plane, those poles or those roots. So now, if we were to look at little s times capital X of s, that would actually cancel this s, so we're okay with respect to checking that second condition of our final value theorem. We actually have that s capital X of s has all of its poles in the left half plane. Or we can now apply the final value theorem, which says that the limit as t goes to infinity of x of t is equal to the limit as s goes to 0 of s capital X of s. That's now the limit as s goes to 0 of 6 s plus 1 over s squared plus 1.5 s plus 0.4. Upstairs, we have 6 times 1, or 6, when s goes to 0. Downstairs, we have 0.4, or 4 over 10, or now we have 60 over 4, and 15 goes into 60 4 times. So in fact, x goes to 15 in the limit as t goes to infinity. And that was determined without finding the exact expression for x of t as a function of time. We just had to use the final value theorem and the fact that s x of s had all of its poles in the left half plane. Let's look at another example. Suppose that now somebody says, okay, here's a transform y of s, given by 1 over s minus 1. What's the final value of little y of t? Well, again, first you need to start looking, are all of the conditions of the final value theorem satisfied? Here, I hope you can see that if you evaluated this for the value of s that causes that to vanish, where are the poles? Well, in this case, we actually have a pole in the right half plane, not in the left half plane. We have a pole at s equal to plus 1. And because of that, we can't apply the final value theorem. We can't use the final value theorem to tell us what's going to happen as t goes to infinity. In fact, you should be able to, by inspection, determine what is this little y of t as a function of time based on that Laplace transform capital Y of s. Well, again, this is an exponential. It's just a growing exponential. It's e to the plus 1 times t for t greater than or equal to 0. And this particular time domain expression, e to the t, is unbounded, or it goes without bound as t gets larger and larger. Now suppose in the heat of the battle you simply applied the final value theorem and said, oh, here's what little y of t will be as t marches off to infinity. So let's just assume that we blindly apply the final value theorem. If one would, let's say, have applied, if one would have applied the final value theorem, then we would have been thinking that here is our conclusion. The limit as t goes to infinity of y of t, but we know this is not true, so let me go ahead and say not equal to, but if we didn't do that, we would say, oh, that's equal to the limit as s goes to 0 of s y of s, and that's now the limit as s goes to 0 of s over s minus 1. Well, the denominator is well behaved. That's just going to minus 1, so that doesn't cause us any problem. The numerator goes to 0, so we would conclude that the final value of our waveform y of t is going to be equal to 0. And that is definitely not what happens. Y of t actually goes unbounded as t goes to infinity. So this is an incorrect result, and the reason it's incorrect is because this started with an immediate violation of condition 2 of our final value theorem, meaning we had an unstable pole and we really then could not go any further. We're not supposed to be applying the final value theorem to that particular transform. If we did, we would be misled and thinking that, oh, everything's fine, y of t is going to go to 0. So let me just say that you can't blindly apply the final value theorem. Let's look at another example. Suppose that now somebody gives you another transform, z of s, and suppose that that's now 2 over s squared plus 4. Now, before you do anything, what are you wanting to do? You're actually wanting to check whether or not z of s has all of its poles in the left half plane, or it does not have any pole on the imaginary axis or in the right half plane. But what happens here? Let's look at the roots of our denominator. Here we have s squared plus 4 is equal to 0. S squared is equal to minus 4. or that now says that S is equal to plus and minus J2. Those now are on the imaginary axis, and one cannot apply the final value theorem. What's happening to this, if you actually looked at this transform, or the inverse Laplace transform of what we started with, which was 2 over s squared plus 2 squared, that's actually the exact Laplace transform of the sine of 2t. And what's that doing as t goes to infinity? Well, sine of 2t just does this. Does it ever reach a limiting value? No, it just oscillates. So we're never going to go to a limiting value as t goes to infinity, which is why we can't apply the final value theorem. This is oscillating. It's corresponding to a sinusoid that will not settle down and reach a final value theorem. And so it's critically important that you check condition 2 in the final value theorem, which is make sure that x of s has no poles on the imaginary axis or in the right half plane before you start applying the final value theorem.